In the vast silence of space, one side of the moon has remained hidden from humanity's eyes since the dawn of time. Until now, China's Chang'e missions, once dismissed as mere replicas of Apollo, have just rewritten history. A Nobel Prize-winning scientist has stepped forward, not with speculation, but with cold, hard evidence gathered from the dark, far side of the moon. Samples have returned, and the early analysis is intriguing. The moon, long believed to be a silent witness to Earth's formation, now appears to be a complex geological puzzle with anomalies, unknown substances, and energy reserves that could influence global energy dynamics. And yet, no one was prepared for what the samples revealed because they raised questions about long-standing lunar theories. While NASA was tangled in political delays and Mars-bound ambitions, China quietly pursued a mission far more strategic. Through the Chang'e program, named after the Chinese moon goddess, they mapped, landed, sampled, and most critically succeeded where no other nation dared: the far side of the moon, a place Earth never sees, a place radio signals cannot reach. And in 2019, with Chang'e 4, China became the first country to land a rover there. But it wasn't just a feat of engineering. It was a statement of intent. With a communications relay set at a gravitational sweet spot beyond the moon, China laid the foundation for full-scale exploration. And when the U-22 rover began transmitting, what it found sent shockwaves across the scientific community: a shiny greenish, gel-like material lying quietly inside a crater, completely unlike the surrounding lunar surface. It reflected light unusually and defied the geological expectations of the area. Though scientists called it impact melt breccia, what truly intrigued them was not its presence, but its freshness. It appeared recent. But how? The far side lacks radioactive heat-generating elements. It should be cold, quiet, and inactive. So why did this strange substance look newly formed? Months after the gel-like mystery, the U-22 rover stumbled upon something even more bizarre: transparent glass-like spheres scattered across the dusty surface. Not fragments, not beads, but perfect orbs measuring up to an inch in diameter, larger than anything Apollo ever retrieved. They weren't scattered randomly. They appeared in patterns, as if shaped by natural processes we don't yet fully understand. These formations challenge our current models of impact physics. Creating such large and clear spheres would require intense heat far beyond what typical meteoroid collisions produce. Some scientists speculated ancient volcanism. Others proposed theories about unknown geological processes beneath the crust. What's clear is this: the moon's far side is not a barren relic. It's dynamic, unpredictable, and likely far more active than we ever imagined. And if natural processes aren't fully responsible for these spheres, what is? But the discoveries didn't stop at the surface. China's mission targeted the South Pole Aitken Basin, one of the largest impact craters in the solar system. Formed by an asteroid strike billions of years ago, the force of the impact was so massive it likely cracked through the crust and exposed material from the moon's mantle. When samples from this region were returned by Chang'e 6 in 2024, what they contained challenged long-standing lunar theories. Scientists detected minerals like low calcium pyroxene and olivine, direct evidence of the moon's deep interior, but their composition was unexpected. They didn't fully match the models. The elements and ratios were different from what geologists predicted based on the moon's formation theory. Either our models need refinement or something altered these materials. And the implications are significant, because if we don't fully understand the moon's formation, then we may need to reassess aspects of Earth's early history. Hidden inside one of the newly discovered minerals, Changbai-ite, was a trapped element that could redefine energy production. Helium-3, rare on Earth, but abundant on the moon. Helium-3 is a potential fuel for clean nuclear fusion. Just 1 ton could theoretically power a country for a year. China's Chang'e 5 mission confirmed its presence and returned samples. Not as a theory, but as measurable, extractable atoms. Mining helium-3 would require massive infrastructure processing tons of regolith, but China is already planning lunar research stations. Their International Lunar Research Station aims to be operational before 2035, with capabilities for exploration and potential resource extraction. This is no longer just a science race. It's a geopolitical competition unfolding on the moon's surface. Whoever develops helium-3 extraction may influence the future of energy. And while the West debates timelines, China is advancing its plans. When the Chang'e 6 samples were shared with a panel of international researchers, one name stood out: Dr. Samuel Reiner, Nobel Laureate in physics and a respected voice in planetary geochemistry. After weeks of analysis, Reiner made a public statement at a scientific forum in Geneva. According to verified transcripts, he said, "If these mineral patterns are accurate, we are looking at complex geological processes arranged with precision, not chaos." Reiner noted that the crystalline alignment in some of the returned minerals resembled structured layering, not random formation. He drew parallels to natural nanostructures on Earth. The materials found may challenge our understanding of lunar geology. And that statement from someone who once led research at CERN has scientists discussing. Because if parts of the moon's interior show signs of complex formation, we're not just looking at geology anymore. We're looking at new questions about lunar history. Among the least publicized instruments aboard Chang'e 6 was a low-frequency ground-penetrating radar meant to map subsurface layers up to 100 meters deep. The data, published in a Chinese academic journal, showed something researchers are still analyzing: layers that reflected radar signals with high precision, almost like smooth surfaces buried beneath the regolith. In a natural body, layers should scatter signals inconsistently. But this data revealed symmetry, parallels, intervals more consistent than expected for random geology. Some of the returns suggested cavities, hollow spaces with no clear explanation. Speculation has emerged about geological formations like lava tubes. Official reports have not confirmed such claims. But the raw data remains, and analysts have noted something intriguing: periodic low-frequency signals near these reflective zones. It's weak, barely noticeable, but it's there, repeating. And as one Chinese researcher noted, sometimes it's the regularity of a thing that prompts further study. You'd expect NASA, ESA, or JAXA to address these anomalies head-on, but since the Chang'e samples were returned, they've been reserved. limited public briefings, few peer-reviewed co-studies, and cautious engagement. Sources within the scientific community suggest that internal NASA communications have advised lunar researchers to focus on verified data regarding Chang'e anomalies until cooperative frameworks are strengthened. Meanwhile, China pushes forward, publishing data in state journals, managing foreign access to samples, and advancing their infrastructure on the lunar surface. Reiner's observations remain under discussion by Western institutions, and this has led some to believe that the discovery is not just scientifically significant, it's geopolitically complex. At this point, we must face the reality. We're no longer in the era of discovery. We're in the era of competition, and China's lunar activities suggest a focused agenda. If the moon contains not just energy resources, but unique materials, then access to those areas isn't just about mining. It's about influence, technological, strategic, and scientific. And if what's buried beneath the far side of the moon is geologically complex, then the stakes are significant. This isn't just about who gets there first. It's about who advances our understanding, what they choose to share, and what remains to be explored. For decades, we looked at the moon and saw a lifeless stone, a dusty echo of Earth's formation. But maybe that was never the full truth. Maybe the silence was complexity, a veil drawn over something more intricate than we understood. China's discovery didn't just dig up lunar rocks. It unearthed new questions that researchers hope to explore. A Nobel scientist, one of the brightest minds of our generation, has shared insights, noting that what lies beneath the far side of the moon may challenge our assumptions. Glass spheres, unusually uniform, signals repeating periodically, geological formations that reflect, align, and resonate not with chaos, but with complexity. If even a fraction of this is true, then we are standing on the edge of a scientific revelation. One that doesn't just change our view of the moon. It reshapes our understanding of planetary science and our place in the solar system. If this information interests you, stay engaged with credible sources to learn more. Comment below. What do you think is beneath the far side of the moon? Share this content responsibly, because advancing knowledge matters. This isn't science fiction. This is science, and the moon is revealing new mysteries.